Yes, students, in lecture 1 and lecture 2 for stability of critical points, I have defined two cases, case 1 and case 2. Now I start the case 3rd. If lambda 1 and lambda 2 are complex roots. Okay, that is lambda 1, you can say that this is equal to alpha plus I beta. Yes, and again lambda 2, this can be written as alpha minus I beta. Okay, now from the lecture 1, you know, x dash is equal to ax, x is equal to ty, substituting this, and y dash is equal to dy, where d is equal to t inverse 80. You know all these things. Okay, and the matrix D is of the form, and the matrix D is of the form, from that case, is of the form D is equal to alpha beta minus beta alpha. Let y dash is equal to dy. So y dash, you can, y1 dash, y2 dash, and y is again y1, y2, and d is here given. Operating this, we get y1 dash is equal to alpha y1 plus beta y2, and again y2 dash is equal to minus beta y1 plus alpha y2. Okay, y1 y2, y1 y2. In this case, solving these equations, we get, in this case, solving these equations, we get, yes, y1, this is equal to e to the power alpha t c1 cos beta t plus c2 sin beta 2. Yes, and similarly y2, this can be written as e to the power alpha t minus c1 sin beta t plus c2 cos beta t. Yes, now let us suppose that C1 is equal to rho cos gamma, and also C2 is equal to rho sin gamma. Substituting here, C1 is here, therefore cos gamma, cos beta 2, here is sin gamma, sin beta 2, and similarly for here, so we get y1t, this is equal to rho e to the power alpha t cos gamma minus beta t. And similarly, here is substituting here, you get sin a minus b, that is the form is you get y2t is again you get it rho e to the power alpha t sin, yes, gamma minus beta t. Yes, now let y1 is equal to r cos theta and y2 is equal to r sin theta. From this equation, it is clear that theta is equal to tan inverse, yes, y2 by y1, and again r square is equal to y1 square plus y2 square, y1 square plus y2 square, and from this equation it is clear that this is again is equal to rho e to the power alpha t, that is you can say r square is equal to this thing. And now take substituting y2 and y1 here, so you see that tan inverse y2 by y1, that is the case for tan inverse rho e to the power alpha t, yes, and sine gamma minus beta t. Yes, again this divided by rho e to the power alpha t cos gamma minus beta t, tan inverse of tan of gamma minus beta t. So you get that theta is equal to gamma minus beta t. Now eliminating t, parameter t, yes, parameter t, we get eliminating t, we get from here t is equal to theta minus gamma divided by minus beta. Yes, this is again is equal to minus theta by beta, yes, plus gamma by beta. Okay, now substituting here, as is r is equal to rho e to the power alpha t, so under root of r, you substituting here, r square is equal to this is square, so you get is r is equal to under root of this, so you get a y1 square, so you get r is equal to this thing, you are not. So r, what is r? R you get y1 square plus rho e to the power alpha t, that is rho e to the power alpha, and now t which is equal to here, that is minus theta by beta plus gamma by beta. So you see that here is rho e to the power minus alpha by beta theta and plus alpha gamma by beta, this is any other constant, so you can say that this is again is equal to k e to the power minus alpha by beta theta, where k, yes, where k is equal to e to the power alpha by beta gamma. And thus this is the equation is like that, spirals, so you can get thus the phase portrait is family of spirals. Okay, that is the case can be written as r is equal to k exponential of minus alpha by beta theta. Okay, now we discuss the case, both the case, that is the case when alpha is less than when case 1, when alpha is negative, or you say that alpha is less than 0 and beta is greater than 0, then these spirals converges towards the origin and the phase portrait in this case is given as stable focus. Yes, stable focus. Yes, and the phase portrait, which is defined as, this can be written as like that. Okay, this becomes a spiral, and all these tends to origin. Yes, y1, y2. And now if alpha is case B, if alpha is greater than 0, and yes, and beta is less than 0, in that case, then these spirals diverges from the origin and in this case the origin is unstable focus, and the phase portrait, which is given as like that, phase portrait is given as this, all goes to this outside, yes, these are goes to away from this. Here is y1 and here is y2. Yes. So I have defined, and the next case, see, if alpha is equal to 0 and beta is greater than 0, then the case, then these critical point, then the critical points critical points 0, 0 is called center and is stable. The phase portrait and the phase portrait is given by stable center. That is the phase portrait, which is defined like that. Yes, this one, yes, and which is defined as the stable, that is all converged. This one, y1 is y2. Yes, yes, student. Now I have defined you all the cases for the cases for the roots when lambda 1, lambda 2 are different from the distinct root, double roots, and also complex root. Now I have defined all these cases. So I defined now some examples. Okay, examples from lecture 1 and this lecture. You can solve so many questions, and there let us suppose the question example. Discuss the critical points and sketch the face portrait of the following systems. From example 1 and 2, I have cleared it. Let us first example is like that. x1 dash is equal to -3 x1 plus x2 and x2 dash is equal to 4x1 minus 2x2. Yes, here you see, if you find the characteristic polynomial determinant of a minus lambda I, so for the solution, yes, and you can also, I have also defined the second one is 2 is, the problem is like that, x1 dash is equal to 3x1 and x2 dash is equal to x1 plus 2x2. Yes, from solution 1 we see the characteristic polynomial which is defined as the lambda determinant of a minus lambda I, you know, this is equal to 0. Yes, and therefore you can find the characteristic substituting here a, you know, from this here is a is minus 3, 1, 4, minus 2, and again x is equal to x1, x2, yes, and x dash is equal to x1 dash, x2 dash, yes. From these you can substituting here, you can determinant of a minus lambda I is equal to 0. So you here see that minus 3 minus lambda 1, 4 minus 2 minus lambda is equal to 0. You can solve this question. If you have solved, this implies that minus 3 minus lambda minus 2 minus lambda minus 1 is equal to 0. Now I think you can solve it, and now you have the equation is like that, lambda square, you get the lambda square plus 5 lambda plus 2 is equal to 0. Now you solve the roots of this. I think the roots are lambda are approximately minus 5, and for the ideal cases, as you can define, the roots are approximately minus, because here you can say minus 5, yes, minus 5 plus minus under root of, yes, 5 minus, yes, here is therefore this minus 4. Okay, therefore you see that if you substituting here is this one divided by 2, you see here is minus 5 and approximately 16, 17 here is when, but 16, therefore taking 4, that is minus 5 plus minus 4 by 2, that is minus half, the minus again minus half, that is you get the roots are like that, minus half and minus half approx. Yes, because here is the clear minus 5 plus minus 17, and now you can take as 16, so you can see that minus half, and that is here you see that is the roots lambda 1 which is minus half and lambda 2 which is minus half, that is the all the roots of lambda 1 which is less than 0, lambda 2 which is again less than 0. Therefore from the lecture 1, you know, these you see that the case in the lecture 1 you see that the system is stable. Yes, therefore you see the system is from these roots, the critical points are asymptotically, in this case you discuss the critical points, so you see that the critical points are asymptotically, yes, stable improper node. From lecture 1 I have discussed this, and you can also define the phase portrait, which is like that. Phase portrait, these are tends to origin, yes, and the phase portrait is defined like that. Yes, this is the phase portrait, and the roots, you can, the nature of roots, you can say that they were stable, asymptotically stable improper. Actually you see the case only this one, From these you can discuss all the nature of the roots. Yes, from this you can. Now similarly from the next question I can also define from next case I have defined you. Yes, from the next case I have defined you the case. Yes, yes, from the yes, the next one example is here is x1 dash 3 x1 and x2 dash is equal to x1 plus 2x2. Yes, from earlier, from the same. Yes, solution of this one, solution of 2 from the as here is a is comparing this a, this can be written as this plus 0x1 0 can be written as 0x2. So a is 3 0 1 and 2. Yes, you can say that, and therefore from this is u, and x dash again is equal to x1 dash x2 dash. Yes, and x is again is equal to x1 x2. So from the earlier you can say that from this example you see that the characteristic polynomial determinant of a minus lambda is equal to 0. So you see here is you have the case determinant of 3 minus lambda is 0 and 1 2 minus lambda is equal to 0, or you get 3 minus lambda 2 minus lambda is equal to 0, that is you get the roots are lambda are 3 and 2. Here you see that the case 1, that is the roots are distinct, but they are lambda 1 is greater than 0 and also lambda 2 is greater than 0. That is, in this case you see that the phase portrait is unstable. Okay, in that case the critical points are, in that case the critical points is asymptotically, yes, unstable improper node. And the phase portrait you can define as the earlier. Here is y1 y2, yes, and these are away from the origin.